All right, thank you. Thank you to Suna for organizing and inviting me, and for people listening. Thank you to Radu, who's in the back, for, let's say, so there are two interpretations, either stealing my thunder for a lot of what I wanted to talk about, or doing all the work for me ahead of time. So we'll take the positive gloss on this. Okay, so by this I mean, of course, you talked a lot about characteristic bisets, and I want to sort of emphasize this word minimal here. But even though you already did a lot of this, I do want to recall, I want to start with a key example that you've talked about also, just to get some to get my perspective sort of in line. So imagine that we have G, our finite group, S, a C log P subgroup of G, and so we want to view G as an S biset, which maybe we'll denote G with some decoration, like this. Okay, and as an SS biset, it's not any old SS biset. It has certain properties which have already been written down, but let's do it again. So the first one that wasn't sort of made that explicit, but is still quite important, or maybe the 0th one. So G as a biset is, in fact, bi-free and symmetric. So this actually, I guess it wasn't stated explicitly, but it does follow from the formulation that Radu gave earlier today. But I want to focus on, I want to just point out that, like I say, bi-freeness is saying that left and right multiplication by elements of S can be canceled, fine. Symmetric, this is coming from the map G maps to G inverse, swaps the role of left and right multiplication. Okay. So that's point 1. Point 2, which way do we want to do this? As was stated, this guy, so if we say F is the fusion system on S generated by, or induced by G, then the biset G is F generated, which means, so if I have an element G in G, little g in G, its stabilizer which by definition means the set of all points, or pairs, UV in S cross S, such that U times G equals G times V. That's the definition of the stabilizer, and is of the form, I guess in the notation that we've seen already, we would call this the subgroup, the twisted diagonal subgroup P conjugation by G. Pairs C of G, U for U in P. Okay, so the idea is that if we have a The notion that I want to emphasize here is that the stabilizers of, well, this biset encode actual morphisms in the fusion system as part of their data. They're twisted diagonal subgroups, and the twisting is going to be a morphism in the fusion system. That's the real key idea that we're interested in here. See if we can do this with the remaining space. Okay. Third thing is that this biset is F stable, which has already been talked about at length, but let's just, so for me this means, and the way that this is easiest to check is, well, for all morphisms phi in the fusion system going from P to S, then I can look at the fixed point sets on G fixed by the subgroup, the twisted diagonal subgroup P phi. And this is equal to the non-twisted diagonal fixed subgroups fixed point set in order. And it's also equal to, if I sort of twist in the other, if I twist in the other direction. Okay. And then the last point is that the order of G modulo the order of S is prime to P. Okay. All right. So those are the key. Those are the points that we're most interested in, and we turned these points, or I guess Mark Linkelman and Webb thought about what bisets are important for understanding fusion systems, and they said, well, these are the key characteristics that we want. So we say definition, a biset, an SS biset omega is F characteristic if it satisfies 0 through 3. That's actually going to come from the fact that in a fusion system it's a divisible. Every morphism in a fusion system factors as an isomorphism followed by an inclusion. So once you have this stability, that's going to give you symmetry, I claim. But yes, I'm going to think about being symmetric as part of the definition. I don't think I'm lying when I say that. But I'm defining my way out of lying, even if I am. Stable meaning, right? So another way of saying this is that if this is an SS biset, I can view it as a PS biset, either by restriction to P or restriction by twisting along P on the left. Those two PS biset structures should be isomorphic and dually on the right. And once you have both of those, that should give you enough to guarantee that you have symmetry. Or you put it in as axiom 0. All right, so that's what it means to be characteristic. And let's just augment this a little bit more. Let's say omega is F semi-characteristic if it satisfies just 0 through 2. So if you like this third condition saying that the index in G of S is prime to P, that's reflecting the fact that S is a C-love subgroup. If we still have a fusion system that we're interested in, and a biset which is F generated, F stable, symmetric, and bi free, then that's almost as good as being, well, it still gives us a fusion system, non-trivial theorem, but it need not actually be saturated in general. Okay. All right, so as has been mentioned a few times, the homotopy theory of fusion systems paper says that if F is saturated, then there exists an F characteristic biset, and Pooch and Ragnarsson, Stanku, as we just saw, shows that the other direction holds as well. That the existence of a characteristic biset guarantees saturation of the fusion system. Okay, so great, and we can go further with this, and we can say, you know, looking. I do want to emphasize that throughout this entire talk, I'm very definitely firmly in the world of actual sets. I'm not working in the sort of Grothendieck group of anything. I'm not p localizing or p completing or anything. I have honest sets that I'm playing around with. And let's just observe why, one reason why it might be nice to do this. So theorem de Park. So given if omega is a characteristic biset, is F characteristic biset, and I form the group G, which I want to think about as the automorphisms of omega that respect, say, the right multiplication by S, but not necessarily the left multiplication. I mean, it's automorphisms of omega that, you know, omega as a right S set, and forgetting about the left S set structure. So this is a group, is a finite group. You can naturally embed S inside it. So let's just say that S embeds inside this group G by means of, I guess, an element of S goes to left multiplication by that element of S. And the fusion system that we start off with is the induced fusion system on S induced by G. So the mantra is all saturated fusion systems are induced by finite groups. And this comes from actually having bisets to play with. And you don't get this if you're working on the level of you know, elements in the double Burnside ring, stable, p-localized, virtual, etc. So we want actual sets to get this. So once you say something big like this, you have to give the caveat. S is not basically ever a Sylow P subgroup of this group G that we're constructing here. So every saturated fusion system comes from a finite group, but not necessarily a Sylow subgroup of that finite group. We already knew that because we know that there exist exotic fusion systems. So.
Okay, so you say basically never?
I mean, I don't know if it's like, if S is the trivial group, like if P doesn't divide the order of, like if you're talking about the trivial fusion system on the trivial group, then maybe you could arrange it so that this is Sylow, but
Okay,
like
right, I understand that, but if you started out with a...
I mean, are you asking the question, like, under what circumstances is S Sylow in this constructed G?
Yeah.
Almost never. In fact, I mean, okay. So the order of G is going to.
Okay.
I mean, G has the structure of a Reith product of S with order of omega modulo S elements. So it's a gigantic group, and usually many powers of P above S are going to divide this. I don't think that there's anything particularly useful you could say looking for the like one counterexample to.
No, okay. Is it known if you can modify the construction somehow so that we actually recover G in cases where G comes from a finite group?
To my knowledge, no. And this is a great question, but we'll hopefully try to get to a reformulation of that later on. All right. Okay, so this is why we're talking about bisets and not something, you know, a little bit more flabby. And and we'll go back to this. Being saturated is the same thing as as stating the existence of a characteristic biset. But of course, in general, there are going to be infinitely many characteristic. If you're saturated, then there will necessarily be infinitely many characteristic bisets for that one fusion system. I mean, even if you're just in the realizable case, you have a group G that realizes some particular fusion system, there are in fact going to be infinitely many groups G that realize the same fusion system, just cross G with some P prime group, right? So it's a stupid example, but it definitely shows that there are infinitely many ones. So the characteristic biset, there is no the in this world. So the F characteristic biset doesn't exist. And by that I just mean it's not unique. Okay, so the claim is that even though, the first idea of this talk is that even though there is not the characteristic biset associated to a saturated fusion system, there is a best characteristic biset, or at least a minimal characteristic biset associated to a fusion system. So I guess you're supposed to put your own name with an initial, fine, whatever. There does exist a unique minimal F characteristic biset for F saturated. And by minimal, I'm not just talking about size. I actually mean it's contained in every other. If you have any characteristic biset at all, it has to contain a copy of this guy. Let's call it omega sub f. So every characteristic biset has some copy of omega sub f of f living inside it. And now I'm talking about on the level of SS bisets. Okay? So it's always there. And the claim is that the idea is that this is, I want to think about this as sort of a minimal group-like structure that's inducing the fusion system, that gives us all the data of the fusion system. It's playing the role of an ambient group, a smallest ambient group, giving rise to the fusion system, even when there isn't such a thing. All right. Been working in a university with no chalkboards for a while. I'm not used to this. Okay, let's take a slight detour to yeah, that's my excuse for the handwriting. If you're it's not the hands, it's the stuff on the board. It's just okay. So I want to sketch out very briefly why this is true. And then I want to, after hopefully doing that in finite time, I want to try to elaborate on why we should think of this omega f as being group-like in nature, and try to explain, the sense in which I mean this. Okay, so why does omega f exist? So we're going to take a small detour to F sets. So in other words, I'm going to drop the left and the right action. I'm going to just say, so now we actually saw this already also, but let's say a left S set X is F stable, or an F set if for all morphisms in the fusion system I can view X as a P set by restriction, or I can view X as a P set by twisting along the morphism in the fusion system phi, and then restriction. And these guys should be isomorphic to each other as p sets. Okay. And so it's probably a good idea to do examples from time to time. And there's only one example that works. So okay, so we're going to look at the fusion systems on D8. So D8 looks, subgroup lattice looks something like this. Let's just say P1, P2. And you might notice that I have strange naming convention. The idea is that the two subgroups of order 2 that are both called Q1 are conjugate to each other in D8. The two subgroups of order 2 that I'm calling Q2 are also conjugate to each other in D8. The one down here. Okay. And we can also look at, so there are 3 fusion systems on D8, as is already up to isomorphism, as has already been mentioned. So we can look at the fusion system on D8 coming from D8 will be in white. We can look at the fusion system on D8 coming from sigma 4, which will be in red. And once I look at D8 embedded in sigma 4, I get new conjugation between Q and the center. And when I move up to the biggest fusion system, which I guess will be blue, F, D8, A6, all of the cyclic 2 subgroups are conjugate to each other. Okay, so yeah, I mean, so we have containments. I mean, and everything that's white should also be red too. But I'm just trying to show where the new, also the blue looks sort of white. I'm just trying to show where the new data is obtained when we look at embedded inside bigger and bigger subgroups. Okay, so for the fusion system coming from D8 itself, well, I mean, F stability is the same thing as just being an S set. There's no condition. I mean, saying that the number of fixed points for one copy of the thing I'm calling Q1 versus the other copy should be the same, that's automatic whenever I look at two conjugate subgroups of D8. So that's not interesting. If I look at F is the fusion system on D8 coming from sigma 4, then we find, I'm going to write, let's say we find a basis for the F sets. And as follows. So I can look at, I'm going to write block brackets to indicate. So this is the D8 set, transitive D8 set with stabilizer D8. So this is the 1-point D8 set. So that's one element in there. I also have the 2-point D8 set with stabilizer P1. I also have P2 plus a copy of Q1. I also have P3 plus a copy of Q1. I also have Z plus 2 copies of Q1 and Q2 plus nothing. Okay, and by basis I mean every. Okay, so here's a bunch of different D8 sets. They're all F stable. You can check on your own time. You can check basically. Okay, once I have one orbit with stabilizer P2, well then I can look at the Q1 fixed points of that orbit, because Q1 is not D8 subconjugate to P2. There are no Q1 fixed points once I start off with P2. Okay, so I start off with the D8 set P2. I ask, is it stable? The answer is no, because there are no Q1 fixed points, but there are Z fixed points, because this is a subgroup of this P2. And these two guys are now fused in the sigma 4 fusion. Okay, so we basically go down and we say, okay, are we stable? No. We need to add something in order to make us be stable, in order to make the S set that starts with P2 be stable. And it turns out that it's enough to just add a copy of the orbit Q1. And you just go down the list and you check that this is the case. And by basis, I mean every F set, every F sigma 4 set can be written uniquely as a sum of these 7 guys, 6 guys, whatever the number is. These 7 guys. So that's the idea. Okay. Similarly, when we look at the fusion on D8 coming from A6, we find a basis with, well, one element for every F conjugacy class of subgroups. So when we go up to A6, there's 1, 2, 3, 4, 5. All the order 2 subgroups are now fused to each other. 6, there exists a basis of 6 F sets. Okay. And again, basis means that anytime I have an F set, an F stable set, it decomposes uniquely as up to isomorphism as a sum of those 6 guys that I'm not writing down. Okay. So this was the sort of basic observation that came many years ago. And then the question was raised, okay, is this true in general? Or is this some, like, just a really small case that nothing interesting is going to happen in? Does the existence of this basis actually reflect a more general phenomenon? And the answer is yes. So Suna proves this behavior is general. So let's write A of F, A plus of F. This means, by this I mean, isomorphism classes of F sets. This always has a basis. Alpha sub P, where P, so indexed by the F isomorphism classes of subgroups in S. And this was, we actually saw a little bit in Radu's talk how this is done. Basically, well, it's actually the exact same procedure that I described up here. You start off, you pick a subgroup. In a moment we'll say that it has to be fully normalized, but we pick a subgroup and we look now at an S orbit of that subgroup. You ask, is it F stable? If it's not F stable, the meat of this theorem, the actual work that goes into it, is showing that if it's not F stable, then there's a minimal way to stabilize it. There's a minimal way that we can add just a single orbit that will sort of stabilize it at the next level. So working from top down, it's stable at the very top. we ask now on the next level down, is it stable? If the answer is yes, then fine, we move on. If the answer is no, then there's a unique choice that we can do this that's not going to sort of screw up things too much as we go along. Okay, so more, I mean, let me say this more explicitly. So these alpha p satisfy, so I'm assuming that here p is a fully normalized representative of its class. Okay, so I'm indexing them not just by the F conjugacy classes, but actually I'm picking representatives in these I'm picking fully normalized representatives in the class that I'm looking at. So there are three things that these guys must satisfy. So if I write alpha sub p as, if I break it up as a disjoint union of, let's say, CQ alpha sub p times Q, then first of all, Cp of alpha, so this is just a coefficient, the number of factors of the orbit Q I have. Cp of alpha sub p is 1, so there's exactly one copy of the fully normalized subgroup that we're starting off with. If Cq of alpha p is not 0, then Q is F subconjugate to p. So I'm only adding orbits that are either subgroups of the original p or they're subgroups up to F conjugation, like we saw up here. When I wanted to stabilize p2, I didn't add any copies of p1 or p3. I only had to add copies of q1, which is now F subconjugate to p2. And finally, if Q is fully F normalized and CQ of alpha sub p is not 0, then Q is actually isomorphic to P in F. So the idea being that not only do we have this basis indexed by the isomorphism classes of subgroups, but in fact we're basically just reading off, we're picking representatives fully normalized in each class, and we can sort of just say, well, pick any numbers that you want for that choice of representatives. You can construct uniquely a minimal F-stable set that has exactly those copies of orbits that we're looking at. All right. Anyway, okay, so that's background. That's Suna's work, or it's part of Suna's work. And then we apply this. We apply this to, well, S cross S sets with fusion system F cross F. It's again a saturated fusion system. And another name for an S cross S set is an SS biset, which, if we are stable in the sense that we're talking about here, if we're for an F cross F set, stable in this sense, that's the same thing as asking that we are stable as a biset for the fusion system F. And I've erased the other guys, but now if we want for the other conditions to hold, so in other words, being F stable is asking to be something that comes from this result that Suna made. If we want to be F generated, then we should only be, if we want to be bi-free, then we should only be looking at stabilizers that are twisted diagonal subgroups. If we want to be F generated, we should only be sort of starting off with actual honest diagonal subgroups without any twisting. So we get, at the end of the day, omega sub p, a collection of guys I'm calling omega sub p, where p ranges over the conjugacy classes of the F conjugacy subgroups of S are F semi-characteristic bisets. And moreover, every F semi-characteristic biset is uniquely expressible as a sum of these guys This is just coming from the fact that the alpha sub p are a basis for the F sets in the one-sided case. And moreover, P divides the order of omega P modulo S unless P equals S. So we have a basis of the F semi-characteristic bisets for all the proper subgroups of S. They do not satisfy the Selov condition, this third point that we were interested in. But for P equals to S, I guess this is unless and only unless P equals S. So the corollary, or the consequence, is that the biset corresponding to the subgroup S itself is characteristic, and it must, at least one copy of it must be contained in every characteristic biset. Okay, so that's where we get the existence of these guys. So now we're saying that every saturated fusion system has a unique smallest biset that's contained in all others. And that comes sort of for free from this work on the freeness of the monoid of just F sets. Okay. Let's so now that so that's the idea. We know that this thing exists now. Maybe let's go back to this example and actually say, so let's not talk about what the bases for the F sets are, but let's actually identify the minimal characteristic bisets for these three fusion systems that we're looking at. So in this example, let's see. So the minimal characteristic biset for the fusion system on D8 induced by D8 is just, well, it's just itself. It's D8 as a D8 biset. Okay, so the minimal fusion system on D8 does not have a very interesting minimal characteristic biset. Fine. The minimal fusion system on the minimal characteristic biset for the fusion system on D8 coming from sigma 4 actually has, so I start off with a copy of, we okay with this notation? Radu was using it before, so I assume that we're good. I mean the SS orbit, where there's a point with stabilizer, the diagonal subgroup of D8. Okay, but this is not enough. We also need to add in a copy of, I have an automorphism alpha 1 of P1, so this is of order 3. So this is the guy that twists the three non-identity elements in the Klein 4 group, which is P1. So I need to have also a copy of P1 twisted by alpha 1, which, by the way, turns out to magically be the same thing. If I view sigma 4 as a D8 biset, that's exactly what I get. So in the minimal characteristic biset for the fusion system coming from sigma 4 is actually just sigma 4 viewed as a biset, not as a group. Now we go up to the biggest, when we move up to omega fusion system on D8 induced by A6. I mean, I'm adding new stuff, so it's not unreasonable to expect that I'm going to just keep on adding to the biset. So I start off with D8 as a biset. I now have information coming from twisting by alpha 1. In the fusion system from A6, I mean, it's now symmetric. So in addition to having this outer automorphism alpha 1, there's an outer automorphism alpha 2 playing the same role. So I need to include that. But we're not actually done. This turns out not to be the minimal characteristic biset in this case. There are also morphisms that come, well, Alperen's fusion theorem tells us that every morphism in this fusion system is a composite of automorphisms of subgroups. In particular, I can look at, let's say, the morphism beta 1, 2. So if you like, this is, I start at Q1, I apply alpha 1 to get to Z, and then I apply alpha 2 inverse, say, to get to Q2. Okay, so I get a map that looks like this. And dually, and then I have its inverse going the other way. 2, 1. And it turns out that if you want to actually get something that's stable, I need to add both copies of Q1 twisted by beta 1, 2 and Q2 twisted by beta 2, 1. So this comes from no group. So the first two examples, the minimal characteristic biset was actually just a group viewed as a biset, but in this third case, there is no group that looks like this. So that's new and interesting, is the claim. All right. So
What's the order?
the order is 8 times 13. Sorry? A6 is bigger than this. So if you play around with so once you know what the order is, you can play around and sort of look at, yeah. Yes, we verified at some point that this guy doesn't come from an actual group. Play with Silov's theorem. 8 times 13. 8 times 13.
Yeah, so that's about 2 maybe.
Am I saying that right? Yes. 4 plus 4 plus 2 plus 2 plus 1. Yes. Okay. Good. Okay. So this is the object that now exists, and now I want to, in the last 15 minutes, try to convince you that it is playing a role very similar to, it is playing a group-like role. Well, let's start off with an easy example. Let's concentrate on this red. Something special is going on with, actually the top two, but something interesting and special is going on with the fusion system coming from sigma 4. This is a constrained fusion system. So let's examine the case that F is constrained. So recall, this means that, so in the fusion system there's a maximal normal P subgroup. I can look at its centralizer in S, and I want for this to be contained in itself. This is the condition that, this is what it means to be a constrained fusion system. So the theorem, BCGLO, I think 1 maybe, 1 or 2. Okay. Says that if F is constrained, then there exists a group, a finite group M, which is P reduced, so it has no normal P prime part. It's P centric. So the centralizer in M of its normal, maximal normal P subgroup is contained in the maximal normal P subgroup. Let's see. And it induces M and S, the C-log that I'm talking about, is a C-log P subgroup of M, and this induces the fusion system. M induces whatever fusion system I started with. Okay, so this was already mentioned that whenever you're talking about constrained fusion systems, they're always realizable. So more, M is unique up to isomorphism. You can make this more precise, but that's good enough for right now. So for constrained fusion systems, not only are they always realizable, but they're coming from an essentially unique group. And it's an essentially unique smallest group. So this is called the, I guess this is the model. So again, in the class of constrained fusion systems, there's a minimal group that's actually giving you the fusion system that we're talking about. So the first observation and theorem, so if we have F is constrained, and I look at its model, and if I look at its model as an SS biset, this is actually the same thing, or isomorphic to, the minimal characteristic biset for F. So in the case when there is a unique smallest group giving rise to the fusion system, that's also the same thing as the unique smallest group-like structure, omega F, giving rise to the fusion system. So that's like one point in our favor to start off with. So I don't want to prove this at all because I'm not doing great on time, but I do want to just mention how we see this, so how to prove. We're going to come back to this original characterization of Suna for what these basis elements should look like, and in particular, we're going to zoom in on this guy right here. So the idea is that it's enough to show so if I have an element M in this model, I want to look at its stabilizer so as we already in the first example we said that the stabilizer of an element is going to be some sort of twisted diagonal subgroup. I mean, what it actually is S intersected S conjugated by M. I mean, the stabilizer is going to be the maximal subgroup of S that's conjugated into S by M, twisted by conjugation by M. You can unravel that at your leisure. But if we suppose that this is equal to the inclusion P, so if I have an element of M whose stabilizer is just it's an untwisted diagonal subgroup for P, then in fact P equals S. So in other words, any time that I have an element of M, I'll just say it that way. So this is the first thing that we need to show, and that this follows directly from the assumption that this follows from the fact that M is P constrained, that the largest normal P subgroup of M contains its own centralizer. Once we have that, if M and M prime both have stabilizers equal to inclusion S, then M and M prime are in the same SS orbit. So I'm only spelling it out even in this level of detail to emphasize what's going on. We're coming back. The way that we constructed the minimal characteristic biset was I started with the subgroup of S cross S, the diagonal subgroup of S. I stabilized it. So I have now one of these basis elements for F cross F. And part of the characterization of what it means to be a basis element from the stabilization is that we can say, well, the fully normalized, we can say the only orbits, the only stabilizers, point stabilizers that show up that are fully normalized have to be the subgroup that we started with. So in particular, if we had some other, the thing that we would be worried about is if there were a proper subgroup of S, P, and a point of M where the stabilizer of M was this particular point stabilizer. So that would mean that we had a copy of one of the other basis elements, one of these other omega P beyond the minimal characteristic biset living in this guy. So that's the first thing. But the other thing that we might worry about is, well, what if even if all points M that have this as their stabilizer actually have the diagonal subgroup of S as a stabilizer, that's still not enough. That's just telling us that M is going to be multiple copies of the minimal characteristic biset a priori. But point 2 says that, in fact, there's only, anytime that we have two elements of this form, I can get from one to the other by multiplication by S. That means that, in fact, there's only one orbit of stabilizer this type, and therefore we're back in the minimal characteristic biset case. Okay. So I use this so I can erase it now. So next, quick example. Let's application to linking systems. So now, let's say that we have LC as a centric linking system. For the fusion system F, which we now know always exists, and we even know that it exists without, or after, I guess tomorrow we'll know that it exists once Justin talks to us. We'll know that it exists even without the classification theorem. Great, so we have it. So Chermak views this guy he doesn't view it as a category. He doesn't think of it as a bunch of different objects and morphisms between them. But he views it as a partial group. I'm not going to say too much about this, but except the following. How we go from the way that we're used to thinking about this as a category to this partial group structure. Partial group means it's a set with a multiplication that's not always defined between all objects. So I take the isomorphisms of the linking system and identify them if one is a restriction of another. So there's a lot of structure theory that I'm glossing over very quickly here, but let's just say you have the isomorphisms in the linking system. you can say what it means for one to be an extension of another, and we're going to identify two morphisms as the same object if one is an extension of the other. We therefore get a finite set of morphisms in the linking system. Non-trivial theorem is that every class so defined, in fact, has a unique maximal element. We then turn this set of maximal non-extendable isomorphisms of the linking system into, it's naturally an SS biset. So these non-extendable isomorphisms form an SS biset. So let's call it, let's just give it a name. Let's say script I. And on one hand, we would like to be able to say something like I, viewed as an SS biset, is in fact the minimal characteristic biset of F. Except that's not true. It's not, that's a lie. We need, we actually only get the centric part of the minimal characteristic biset. So this is the centric part. So we can go back up to this A6 example again to see what's going on. By centric part, I mean the stabilizers involved. In every stabilizer, there's a group and a twisting. I'm only looking at F-centric groups that show up. So in the A6 example, when I take the linking system for A6, centric linking system for A6, and view it as a biset, this is the centric part here. I only get the only centric subgroups are D8 and the index 2 subgroups. The order 2 subgroups are not centric. They're not seen by the linking system. The linking system doesn't have these guys down here as objects. It has no way of actually knowing anything about the fact that I mean, basically the issue is that the linking system knows that there is the centric subgroup P1. It knows that P1 has an automorphism, alpha 1. It also knows the same that P2 exists and alpha 2 exists. But the linking system doesn't know that it makes any sense at all to compose alpha 1 and alpha 2. The composition of these two guys lives down below the centric level. So it's not seen by the centric linking system. Okay, so it's missing. And so the centric linking system can't identify the fact that there are actual morphisms that come from the composition of alpha 1 and alpha 2. But the minimal characteristic biset has to see those guys. It must recognize not just alpha 1, alpha 2, but also that the composite is a morphism in the linking system, and that we want in the fusion system, and that we want stability to hold on the level of all morphisms. So in this particular sense, you could almost say that there's, in this very narrow sense, there's more data in the minimal characteristic biset than there is in the linking system. It sees this additional stuff below the centric level. In the much deeper sense, there's a lot more information in the linking system because there's the biset doesn't have any sense of composition between these guys a priori.
But also you can recover, I mean, just the centrics, that determines fusion by algebraic fusion system.
Yes, you can.
So the information must be there somehow.
I mean, right, I mean, okay, well yes, this is true. The information is always there. I mean, but this is I guess this is a little bit like saying that after Andy, I don't know, like,
maybe the subcentric linking system.
That's a good question. I don't know what happens if we look on the subcentric levels.
Actually, you know that from the quasi-centric linking system you get the quasi-centric part of the minimal.
Oh yeah, centric quasi-centric.
Yes, okay, we did that, but I thought that subcentric was even more was more general than that. So
But in this case, it's a
Okay, point taken. I mean,
you could also model that by field 3F2 or something like that. That would be there. What would the subcentric?
okay. I had one more section, but I also have negative 1 minute, so I think I'll just end the talk at this point. So, and we can talk more about this later. If
Are there any questions from Matthew? For Matthew?
I mean, you're right. You're right that the Alperen's fusion theorem says that the data is already in the linking system. I guess it's sort of a question of how do you extract it.
Right.
I mean, oh, sorry, I should have shout out to Ergun and Suna. In joint work with Ergun and Suna, we also got a we also, in a certain sense, were able to compute the structure of the minimal character. We were able to compute the structure of these basis elements alpha p in terms of the shape of the fusion system and additional data and sort of certain combinatorics. But it's not an easy picture. So in the same sense, saying yes, there's enough data here plus Alperen's fusion theorem to say what the other morphisms are. It's not easy to go from there to say what the actual minimal characteristic biset is. Right? It's not enough to just say, well, these are morphisms that live beneath the level of the centric subgroups. Some morphisms that live beneath the level of centric subgroups are going to show up. Some of them will show up sort of with multiple copies. Some of them won't show up. Exactly which is which is a very complicated question.
There's sort of an algorithm for finding.
There is an algorithm. There is an algorithm, that's true.